Alright, hey everybody. This is the review sheet for the Unit 1, Topic 1b test. That test is coming up this Thursday, and by no means should you only study this test review. This test review is short, not particularly comprehensive. If I were you, I would study this test review and the Unit 1, Topic 1b quiz. That's the 25 pointer. Surely you'll study that, and you'll study the packet, the Unit 1, Topic 1b packet, and all the homework found therein, and all the many problems found therein. And I'd consider reaching out to my teacher for extra help too. Not extra help, but extra practice problems. I'm sure we could throw you a Delta Math. I'm sure we could clue you in on what maybe the bigger objectives to focus on are. But for sure, don't study just this. If you do, you'll find yourself probably underprepared. Okay, anyway, let's go. Let's do it. So number one says, given h of x is f of x with the transformations listed below, h of x equals. Obviously, what they want you to do here is define h of x in terms of the function f of x, which means that you have to apply various transformations. There's probably an a value, there's probably a b value, there's probably a c value, and there's probably a d value. I would think that by now you know the effect of all those things. Hopefully. Let's find out. Alright, so if I have a vertical dilation by a factor of 2, a vertical dilation by a factor of 2 seems to imply that A is 2. That's easy enough. I mentioned this in class, but where it says down 1, if I'm asking you to describe transformations, make sure you don't ever just say down 1. Make sure you actually include some verb. So this is a translation down 1, and that implies that D is negative 1. If we reflect over the y-axis, let's see, whatever could that mean? The y-axis. If I reflect over y, then I'm changing the sign of x, right? If we were started at x, we end up at negative x, or vice versa. To change the sign of x, you want your negative sign to be applied before the function is applied, so that's got to be the b value. So reflecting over the y-axis means that b is negative. If there's a horizontal dilation by a factor of a third, I don't know. Let me keep just modeling my thinking here. You guys probably are good at just memorizing what thing is which, but never a bad idea to have a fallback plan. If I've been horizontally dilated, meaning if I started with a parabola, but somebody grabbed it and crushed it, like so. Horizontal dilation by a factor of a third means that this happened. Squish. Would stay symmetric to the y-axis, by the way. But if that happened, then what happened? Well, again, it's x's. It's x's that got changed. So it's got to be one of the variables that still applies to x, meaning it's got to be one of the inside variables. So it's b. And then the big thing to remember is just that b is backward. So if I'm trying to get squished by a factor of a third, then you need a b value that's actually greater than 1. So you take the reciprocal of the number you see here, and that's telling you that b is 3. Now again, taking that in conjunction with the reflection, we know that b is actually negative 3. So let's say the absolute value of b is 3, but we know it's negative because there's a reflection happening. And finally, we've been translated to the right by 4. And being translated to the right by 4, that's a c value for us. And those c values, again, are kind of the counterintuitive ones. You would think that to go to the right, you would add 4, but you want to subtract 4. But wait, the function already has a minus in it. So actually, c is a positive 4. It's just when we plug it in there, it'll look like a minus. Okay, that was a lot of time spent on a problem that you probably didn't really need all this time spent, but your final answer should be to us that h of x is equal to 2 times the function f of, what did we just say? Negative 3 will be our b value times the quantity x minus 4. Close, oh, that 4. These 4s always come out weird on my tablet, sorry. 4. And then down 1, so minus 1 on the outside. But there it is. That's all we needed here. Before I move on, I don't actually know what numbers 2, 3, 4, 5, 6, 7, 8, 9 hold, but if I were you and I was preparing for a math test and my teacher gave me a practice problem where the transformations were described and I had to write a rule, I think I would make sure that I was prepared to take a rule and turn it into transformation steps. I'd make sure I could do it that way. Just a rule of thumb, I think as you prepare for any pre-calc test going forward, you better take all these problems and at least reverse them. Make sure you can go the other way. So can you go from described transformations to a rule? Okay, great. Can you go from a rule to describing the transformations? If you can do both, then you're going to be much more prepared. Moving on. All right. Oh, no, that was supposed to be a surprise. Okay, hide that. All right. Hey, look, it's number 2. For number 2, you guys have a graph to look at. You have a function rule. And we're supposed to answer questions about this. So it says, first, write the transformations of f of x. So perfect. That's what I was talking about just a second ago. So from this, I think we all said that the first thing you better do is actually factor out the b. Because remember, our general rule says that a times f of b, and that b is always factored out. So if you're given a function like this where the b value, meaning the coefficient of x, is not factored out, then the first thing you should do is factor it out. Hold on one second. Make that thing go away. All right, so it'll be negative a half times the function f of. The negative a half factors out. When you factor out, you're essentially dividing by this value. So obviously on the x, you're dividing by negative a half and it just kind of falls away and you get the x. The 1, you're dividing 1 by negative a half. So it's like you're multiplying by 2. So the negative negative will turn to a plus, and we're doubling this essentially to get to 2. Don't be too proud to just actually distribute this thing back in and make sure it works. Because I've seen plenty of people try to factor out a fraction and they do it wrong. They do it the wrong way. So just distributing this back in, you get negative a half x minus 1. You know you factored correctly because now when you distribute it back in, it gives you the right thing. Just a little quick trick to make sure that nobody makes a silly mistake. Okay, anyway, now that we've done this, it says write the transformations that would result in order. On somewhere, I think in our packet, and I know on the test, it says write it in an appropriate order, because we know that the order, there's many different orders you can use that are all correct, and the general rule of thumb that I've been giving is just do the translations last. Just make sure you translate last, because if you translate first and then dilate, then the effect of that dilation is kind of multiplied by the fact that you've translated first. You're now dilating a bigger number and it has a greater effect. So it's just always wrong to translate before you dilate or to translate before you reflect. So make sure you just do it last. And then, I don't know, lots of people pointed out to me, doesn't that mean we can literally just go in A, B, C, D order? Because if C and D are the translations, then you just go in A, B, C, D, then you're always doing them last. And yeah, sure, that's fine. You could do that. So I'll take that same advice and we'll do it. So remember that A represents two different things. Because it's negative, it's a reflection over. Now a negative A value is changing Y values, so that's a reflection over the x-axis. Then the 1/2, that's less than 1, and it's changing Y values, like we said, because it's on the outside. So that means it's a vertical. It's technically a compression, but I'm saying you should always just say dilation. And it's a vertical dilation by a factor of, so just say BAFO. And with vertical dilations, you just give the A value. Don't take the reciprocal of it, just say by a factor of 1/2. You want to be compressing, so you want a number here that's less than 1. So it's a vertical dilation by a factor of a half. That'll be a compression. If you really want to go above and beyond, maybe in parentheses you can write compression. If you really feel bad about saying dilation and not actually stipulating whether it's a compression or a stretch, then by all means put it in parentheses. All right, that covers A. Let's cover B. B is again representing two different transformations. It's another reflection. This time, because it's a reflection on the inside, that means it's still affecting x values, which means it's going to reflect us over the y-axis. When you change the sign of x, you reflect over the y-axis. All right, it also represents a dilation, but because it's affecting x's, it's a horizontal dilation. So it's a horizontal dilation by a factor of. Now this is the one that's kind of backward. If the number is a half, if that's less than 1, then that actually stretches us. So that means it's a horizontal dilation by a factor greater than 1. And to turn this number into a number greater than 1, you take the reciprocal of it. And you say by a factor of 2. So that's a stretch. Okay, cool. Now what? Oh, the 2, of course. So I see a plus 2. So that means I'm being translated 2 units. And again, this is kind of counterintuitive. If you see the plus, you might think you're going right, but you know you're going left instead. And again, if you want this to feel less counterintuitive, then just think about the fact that if you see a plus 2, it means that your C value must be negative 2, because it turned the negative in our rule into a positive. And then the negative 2 pulling us left means, that feels fine. All right, finally, we've got a translation 1 unit up. There you go. There's all your transformations. This is literally the most there could ever be, because we've got both reflections, both dilations, both translations. When I say both, I mean we've got, vertical, horizontal, vertical, horizontal, vertical, horizontal. Anyway, there you go. I don't know if anyone even needed help with this. This is one thing that you guys all tended to do well with. And I also realize my face. No, it's not really blocking anything. There you go. Now you can see it all. Okay, anyway. You're supposed to find the domain of H now. And to do that, I think you guys did okay with this too. This was on the Delta Math exit card that we did, the little 8-pointer. So basically, to do this, you start by finding the domain and range of the given function. This function here is f. So if I want the domain of f, you just literally read it off the grid. We can see that we stretch from 1, 2, 3, 4, negative 4, 1, 2, 3, 4, 5. So negative 4 to 5. And the range of f we can find easily as well. You just read off the y values. 1, 2, 3, 4. 1, 2, 3. Okay, so that's pretty exciting. Just 100 million 4s. All right, so now what do? Well, now you just apply all these transformations here. So this is where whether it's vertical or horizontal matters quite a lot. So let's highlight all the things that are whatever. If I reflect over the x-axis, then that's going to change y values. So that's a range thing. So what else affects range? Anything vertical. So a vertical dilation is going to change range values. A reflection over the y-axis? No, that's going to be domain, because reflecting over the y changes x values. So that's domain. Horizontal dilation, that's going to affect x values. So that's another domain thing. Translating 2 units left, that's x's. That's another domain thing. And then translating 1 unit up, that is a range thing. All right, so again, just to maybe make clear, I know I said translate last. That's not totally true. There's some logic in taking all of these. I'm not going to really be able to do this, am I? This is not worth my time, but you know, I'm going to do it anyway, of course. Alright, maybe that did it. So can I grab only these green things? Almost. Well, I'm committed now. Alright, you. Get separated. Alright. Yoink. Haha. Alright, so, I don't know. Now maybe you guys can better understand that these transformations come in sort of vertical and horizontal camps. And so when I say translate last, I mean make sure you do any vertical translations after you do the other vertical stuff. Make sure you do your horizontal translations after you do the other horizontal stuff. So if you describe your transformations in this order, that would be fine. And this is what I tend to prefer to do, is to describe all the vertical transformations together and then describe all the horizontal transformations together, just making sure that the translation is always sort of third in that list. Okay, anyway, let's just do this, because most of y'all are fast forwarding through this part of the video anyway, because it's pretty simple. Alright, so let's do this. If I'm reflecting over the x-axis, then that's going to change my range. I don't love that both of these numbers are 4s, because that kind of masks what's happening. But remember, as part of the reflection, these numbers kind of flip-flop too. Think about it like this. If you were at 2, -2, and, I don't know, 5, then when you reflect, your +5 is going to go boop, boop, down to -5. And your -2 is going to go boop, 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 to +2. And so suddenly your domain that went from -2 to 5 now goes from -5 to 2. So it's not just that the numbers get their signs changed, it's also that the max became the min and the min became the max. So make sure you hit that part. But for us, that's going to be a little bit hidden here. In fact, it's going to seem like nothing happened when we reflect over the x-axis, because this range is going to actually just still be -4, 4. Okay, and whatever, that's fine. Now let's do a vertical dilation by a factor of 1/2. That just means everything gets chopped in half, literally. So this value that was at -4 will be at -2 now, and this one that was at 4 will go to 2. And then translating 1 unit up just means adding 1 to the y values. So -2 goes to -1, and 2 goes to 3. This is now the new domain. Sorry, this is the range. And it's the range of our new function whose name was h. So this is the range of h. And we just do the other one the same way. So let's apply all of the horizontal transformations to this domain. And if I reflect over the y-axis, then suddenly the max at 5 becomes a min at -5. And the min at -4 becomes a max at 4. And then we do a horizontal dilation by a factor of 2. That means we're stretching. That means we should now have a minimum value of -10 and a maximum value of 8. And when we translate 2 to the left, everything gets 2 subtracted from it. So -10 drops down to -12, and 8 drops down to 6. But that should do it. That should be the domain of function h. So there. And again, my face is blocking, not much, just blocking the word stretch, which you don't really need to see anyway. Okay, so what's left? What's left is to actually sketch h, which is kind of a pain in the rump. So the good news is, at least, that while you guys have a terrible looking graph, I have a lovely graph. See how nice that is? Now, can I just bring this forward to cover this crap? I can't even grab it. Reorder, top layer. There we go. So there's our graph. So how do we do this? Well, we were talking in class about how what you probably want to do is pluck all 4 of these points and just apply these transformations to the coordinates of those points. And I was doing that in this big table. And I don't think people were super jazzed about that idea. But I just don't have a better idea. So I'm going to stick with it. So what are those points? I don't know. Let me just go get them from Desmos. These points. All right. So -4, -2. Oh, the 4 thing. So frustrating. Okay. So there's our 4 points. Now we've got, what, 6 different transformations to apply here. So this is going to be a bit of a pain in the rump. But let's see if we can't find a shortcut. Let me explain it the same way I explained it in class, first of all. And just say, I guess we need a gigantic table. A table where we're listing all of our ordered pairs. And then we're just applying all 6 of our transformations. So plenty of room. Choppy. Chop, chop. Chop. And chop. All right. So what are all of our transformations? We said we want to, if you actually kind of follow this list and keep to your horizontal stuff and your vertical stuff, then you know all 3 of these transformations will affect the y values, and all 3 of the green ones will affect the x's. So that means I can just sort of change y, change y, change y, and I can change x, change x, change x, and finally in the final column I'll have the correct new coordinates. So I'll stick with that plan. So yellow. Let's make a dark yellow that's actually usable. It's kind of a weird dark yellow, but let's see how that even writes. All right, so what are we doing first? Reflecting over the x-axis. All right, I think I already told you how this works. I don't know, I teach geometry, and we happen to be doing this right now, and somebody was mentioning that they actually still remember this rule. So what happens when you reflect over the x-axis? Well, think about it. Just your y's change. So you would leave x alone, and you'll just change the sign of y. And that's what's happening. And if you get that, then you can just run down this column super fast, and you know that your points are now -4, +2, -1, -4, 2, 4, and 5, -2. Okay, that's the reflection handled. Now, we've got a vertical dilation by a factor of 1/2. So what's that going to do? Dil by 1/2 vert. Well, that's going to take our ordered pair xy, and it's going to map it onto, again, a point where the x doesn't change, but literally all the y's just get chopped in half. So now just do that. But don't do it to the first column, do it to the second column. We sort of keep applying these changes. So it'll be -4, 1. It'll be -1, -2. It'll be 2, 2. And it'll be 5, -1. Okay, then we have a translation 1 unit up. So I'm just going to write 1 unit up. That's pretty good shorthand. How's this work? Feel like you take your ordered pair, and again, you won't change x at all, and to go up 1, you'll just take your y coordinate and add 1. So all of these transformations have an associated coordinate rule that you may or may not remember from geometry. Ideally, you don't need to really remember this rule. You just need to know how to do it. So what is it? -4, 2. -1, -1. 2, 3. 5, 0. All right, that's it. That handles all the transformations in the y direction. We reflected, so the signs changed. We dilated by 1/2, so they all got chopped in half. Then we went 1 unit up, so I added 1 to all the y's. Now I just have to handle all the x transformations, and we're reflecting over the y-axis. So what's that going to do? I bet it's going to take xy, and I bet it's going to map it onto the opposite of x, but leave y alone. And then our dilation BAFO 2, I bet that's going to take xy, and I bet it's going to map it onto twice as much as x, but leave y alone. And translating 2 units left, I bet that's going to take our original, or it's going to take the point from the previous column, and it's going to just subtract 2 from x and leave y alone. Okay, so let's do it. Let's change the sign of all of our x's. We get +4, 2. We get +1, -1. We get -2, 3. And we get -5, 0. Then we're doubling all the x's. So we'll go to 8, 2. We'll go to 2, -1. We'll go to -4, 6. And we'll go to -10, 0. And then finally we want to go 2 units left, so let's subtract 2 from all of our x's. So we'll go to 6, 2, 0, -1, -6, 6, and -12, 0. And unless I made some boneheaded mistake, that ought to be it. So those 4 coordinates in the last column should be all we need. Those guys, right there. Ah, no, my face. All right. Yoink. There you go. So there's all the coordinates that we need. And then just plot them. And I know that your grid isn't great, but my grid is great. So I'm just going to bring it down, I guess. Oh, I made it. Oh, you're so dumb. Okay. Bring this down. Move it to the top again. So it covers all that. I don't care about the table anymore. All that we ever really needed was the coordinates of the final points. So I can plot those points now and we can be done. So I'm going to do that. So 6, 2, 6, 2, that's right there. 0, -1, that's right there. -6, 6. That's right there. And -12, 0 is right there. All right, and then you just connect the dots and pray that you did it right. Oh, come on. My lines are going behind. Okay, I guess I have to freehand this then. It's not gonna look great. Not so bad. Also not atrocious. And passable. Alright, I think that's right. It's probably right. The world may never know. Anyway, there you go. That's my advice. I think I said I'd try to give you a way to do this faster. And the only way I can think to do this faster is maybe try to just do it in bigger chunks. Remember all this yellow stuff? What's one rule that'll just map our point onto the right point? Well, let's see. They want us to reflect over the x-axis, so you better change the sign of x. They want us to dilate. Okay, then I guess do -1/2 of x. And then they want us to go, oh, wait a minute, Mr. F. Those are all y values, of course. So we know that we're leaving x alone. And then we want to go -1/2 of y. And then we want to just add 1. So you can kind of just write one single rule that takes all the y's and turns them into the new y's using the y affecting transformations. And then you can do this all at once. Instead of messing with 3 separate columns, just do it all at once. And if you can do that for the y's, you can do it for the x's too. So we know that xy would map onto, geez, let's see. Reflect, so -2, so -2 times x. Then we want to go 2 units to the left, so subtract 2, y. So there you go. You can kind of think this all the way through. And guess what? If you can do the x's and y's separately, then you could really just do the whole thing with one super rule, where the x's all become negative 2x minus 2, and the y's all become negative a half y plus 1. And this one super rule takes your original coordinates x, y, and maps them directly where they ultimately need to go. So again, however you're comfortable doing this is fine by me, and it's probably fine by your teacher too. I don't believe any of us are going to actually ask you to build this whole multi-columned chart where you literally come up with the coordinates after every single transformation. That's overkill. I wonder where this was supposed to be. Negative 12, 0 is that point, so it's supposed to be right there. All right. Well, that could be a new personal record for talking about a problem that everybody knew how to do anyway for the longest amount of time. Maybe you guys pick something up from it though. Let me know if you actually learned something new from this discussion. All right, moving on. Number 3. It says if the f of x has a domain at negative 2, 6 and a range of negative 1 to 7, and h of x has this formula, oh, then what? Then what? Oh no, there's no question. I'm sure it's fine, the new domain and range, right? Which I'm sure you guys are good at anyway, because I think you already said so. Why don't we play a little game called... No, I don't want to play that game. I was going to say let's play a game called Write Another Rule for mapping the coordinates of f onto the coordinates of h. But no, that game doesn't sound fun. Let's just do the domain and be done with it. Okay, so what's happening? I don't know, maybe I am into that game. I think we should at least list the transformations. I think it's definitely in your best interest to make sure that you can at least write them out in words. So even though the question isn't asking you to do that, you guys know that we're going to ask you to. So breaking this down, this is negative 2 times f. Factor out the 1/3. That leaves x. Now remember, you're dividing by a third, so that means you're really multiplying by 3. So this goes to plus 18 plus 4. Again, there's no way you should ever get this wrong if you just take my advice and distribute back in to make sure that it really works. And then obviously a third of 18 is 6. What do you think people do, by the way, to screw this up? They just take a third of 6. A third of 6 is 2. And then they put a 2 here and they walk away thinking they've done a great job. Well, if they just took 5 seconds to distribute this back in, they'd see that when they distribute it back in, they've got a 2/3 sitting there instead of a 6. And it's pretty obvious that they've made a mistake. So just check your work. It's not that hard. All right. So anyway, if I'm going to describe these transformations in a proper order, we said A, B, C, D is a perfectly proper order. But I don't like to do that. I do like to sort of work from the inside out, making sure that I do the B value before the C, because I'm supposed to translate last. So if I'm doing this my way, then I'm going to reflect first. And if I'm changing the sign of x values, then I'm reflecting over the y-axis. Then I have a horizontal dilation by a factor of. Now this says a third, but we always use the reciprocal, so it's actually by a factor of 3. Now I can do the horizontal translation, and that's fine because I've already done all the other horizontal transformations. So I can say translate 18 units. And what is it? A plus, so I guess we're going left. Okay, so now I start working my way out of the function. We're going to talk about A, and it's another reflection. This time over the x-axis. And then it's another dilation, but this time it's a vertical dilation by a factor of. And this time if it says 2, then it's 2. We're stretching. So don't take the reciprocal of a when you're listing its effect. And finally, translate 4 units. And if it's +4, then it's 4 units up. All right, there it is. Just make sure you're able to do that. This should really be easy money on the quiz, is just describing these transformations. Okay, now let's apply those transformations to our domain and range. If the domain of f is -2 to 6, then again, taking this just kind of one at a time, the reflection means that we now have a minimum at -6 and a maximum at +2. Then the horizontal dilation by a factor of 3 triples everything, so we go -18 to 6. Then translating 18 units left means everybody gets dragged 18 units to the left, and we go over to -36, and then we go over to -12. And this is now the domain of the function whose name is h. And then we can do the same thing for the range. So starting with the range of f, which is given to us to be -1, 7. Then again, we have the reflection happening first, which is going to turn our min into a -7 and our max into a +1. Then we get vertically dilated by a factor of 2, so everybody doubles. -14 to 2. And then we get translated up, so everything gets 4 added to it. So -10, 6. And now that's the range of function h. And that's it. I think this is probably straightforward. Moving on. Okay, so this is where a lot of people definitely had a lot of difficulty. So we'll probably end up spending a lot of time here. Let's find out. A says find g of f of x and simplify completely. So this, of course, is, you know, the write a rule to model thing. So this is the wording from previous quizzes, is we asked you to write a rule to model the function defined as g of f of x. Again, you know, this might get its own new name. We might say, okay, there's a new function, a third function called h of x, and it's defined to be g of f of x, which I'm sure you all remember means g composed with f of x. We've got the two alternate notations that just mean the same thing. And in either case, we're taking f as the inner function, g as the outer. So I typically start with the outer function and I go, okay, all the x's just become empty spaces. And into those empty spaces, we're plugging the inner function, which is f, so x plus 2 over x squared. All right, now I'm supposed to simplify this. So with these complex fractions or these compound fractions, your first step for sure is to get your two terms together. So x plus 2 over x squared, that thing's good to go. But this 1, treat it as 1 over 1. Your common denominator is going to be that x squared, so it turns into x squared over x squared. And a similar thing happens in the denominator. This 1 is also going to get expressed as an x squared over x squared. Now I'm subtracting the x plus 2 over x squared. And just be super careful as you subtract this, because you're subtracting a binomial. So of course, this subtraction sign has to affect both the x and the 2. So don't make a mistake there with your algebra. All right, continuing just across. You know that you're going to end up with a big complex fraction still. The numerator is just going to have that x squared as its denominator. And upstairs, when I go to combine everything, they're all different terms. So you just end up with the quadratic x squared plus x plus 2. In the denominator, you have another fraction whose denominator is just x squared. Then you end up with x squared. It's going to be minus x and minus 2. Minus x minus 2. From here, I hope you all remember that you can just cancel the x squareds. Essentially, you're just multiplying by x squared over 1 over x squared over 1. And so if you multiply through by that, then all the x squareds can cancel. That's one way to think of it. And then another way to think about it is maybe, I don't know, maybe the better way, which is just that anytime we've got these big complex fractions, you're always taking the numerator and instead of dividing by the denominator, you're multiplying by the reciprocal of the denominator. So you've now got an x squared upstairs and an x squared minus x minus 2 downstairs. And as soon as you see it like this, hopefully it kicks in that yes, of course, I can cancel these x squareds now. I'm cross-reducing. And again, I'm cross-reducing because basically, at this point, this is really just all one big fraction now, right? It's a fraction that has these two factors in the numerator and these two factors in the denominator. And of course, I can cancel these common factors. So x squared, you're gone. That's a very long-winded explanation of why you can definitely cancel those x squareds. Anyway, from here, yoink, let's come way back over here. So we've got plenty of room. You better factor those numerators. I think they're both factorable. So in the numerator, you're getting, numerator's not factorable. 2 and 1. 2 and 1 are either giving 3 or negative 3. So no, numerator's not factorable. And I don't need parentheses around it. Denominator is factorable. X minus 2, x plus 1. So we did it. That's our function h of x, where h of x is defined as the composition of those two things. All right, so I did it, and I guess I simplified completely because the numerator didn't factor. If the numerator did factor, I would have to factor it. And if any of the factors in the denominator canceled, I'd have to list any restriction that we lost by doing that. What do I mean by that? I mean, just like we saw in the quiz, we had like, I think it was like I think we had like a 3x plus 12. And then in the denominator, I don't know, we had some quadratic that, let's say, it factored down to x plus 4, x minus 2. Well, if you factor out the 3 from the numerator, which a lot of people forgot to do, but if you factor out that 3, then you find that the x plus 4 in the denominator cancels with the x plus 4 in the numerator. And so you end up with the simpler expression 3 over x minus 2. Well, don't forget, this expression, it's quite clear that x cannot be negative 4 or 2. Over here, it's clear that x cannot be 2, but we've lost the fact that x can't be negative 4. But for this expression to be equivalent to the first expression, we need for this guy still to be undefined at x equals negative 4. So technically, in your simplified expression, you should have some little stipulation over here saying, hey, by the way, don't let x be negative 4. You don't have to mention the 2. That's already obvious. It's clear that this expression is undefined at 2, but this expression would otherwise be defined at negative 4, and we need it not to be, so you better stipulate that it's not. Okay, now again, all that is a moot point because the function we have right here, we don't have that issue. But again, you guys are thinking ahead to an assessment where that issue might be relevant. And now this is attached to everything. Detach. I think it's all detached now. Because I'm going to take all this now, throw it in the garbage, because that was just an aside. All right. Part B says state the domain of g of f of x. And I would caution you against giving the domain by just looking at this function. If I just look at this function, then it's irrational, and I would say that the domain is all reals except, the two zeros of the denominator, which are -1 and 2. By the way, these are supposed to be in numerical order, so don't say 2, -1, say -1, 2. Alright, I would caution you against doing this, because oftentimes you might be missing something. Now, I'm not sure if we are, but let's go up and see. A better, more comprehensive way of making sure that you have the right domain for a composition is you better start by looking at the inner function, which is function f, which is undefined at 0, right? So we missed that. In our domain, our inner function is undefined at 0. We haven't lost that. We still do need to be undefined there. So something happened in the algebra that made us think that we are defined at 0. Now, I shouldn't say something happened. We know exactly what happened. We canceled this factor here. This factor here is the guy that makes us undefined at 0, and it got canceled. So we lost that. And if you don't give that in your domain, you're obviously not getting full credit. So you better put that restriction back in. Now are we good? Now we're probably good. The only restriction on f was that x can't be 0. As you head to g, we see that x can't be 1, but that 1 has to come from this. So technically you could go x plus 2 over x squared equals 1, and really it can't equal 1. It must not equal 1. You could solve this equation, but if you solve it, you're going to get the 2 and the -1 from this denominator. There's not really a reason to try to solve this equation to figure out your further restrictions. They're sitting right there for you. We can rest assured that those are the two solutions to this equation anyway. So there's your domain. It's actually all real numbers with 3 restrictions, not just 2. So that's part B handled. And then part C says find the inverse of function g. Okay, let's do it. So that's g. Oh, I guess I didn't need to do that because there's g right there. All right, anyway, to find the inverse of any function in the world, you're going to just kind of invert the x and y variable. So if g of x is the fancy way to say y, then turn that into x. And all the x's turn into y's, so this is y plus 1 over 1 minus y. That's the initial setup for any inverse. Now if you're trying to find the inverse of a rational, then you might want to throw this over 1. You might want to multiply through by the LCED, so 1 minus y. And you'll do that on both sides, 1 minus y. And what happens over here? They cancel. What happens over here? The x distributes in. You get x minus x times y equals y plus 1. Alright, and I'll admit, what really happened over here? Did I have to multiply through by the LCD? Or can I just imagine cross-multiplying? Yeah, you can just imagine cross-multiplying. Just check this over 1 and cross-multiply. Just know that cross-multiplication is not a real mathematical operation. What's really happening is you're multiplying through by the LCD. But whatever gets you to the next step. We said the next thing to do from here was make sure that any term that has a y in it is together on the same side. I don't care which side, but I'd like to think it's obvious that this guy with a negative coefficient, let's add him to both sides. So we end up with a y plus xy. And then this x is positive, it'll stay positive. The plus 1 turning into a minus 1, that's no big deal. But this is what I would do. Now what? Now you factor out the y. So you've got x minus 1. Factoring out the y leaves you with 1 plus x. And then you just divide through by the 1 plus x. So you get an x minus 1 over 1 plus x, which I would clean that up to x minus 1 over x plus 1. We do want to see descending order. And then the y, I'd clean up the y too, because yes, this is equal to y, but now is a good time to switch back to the proper notation of G inverse. So there it is. That's the inverse. Let's not forget that often when you find an inverse algebraically, there could be issues with the domain and range. There could be issues where the original function's domain does not perfectly map onto the new function's range or vice versa. So it wouldn't be the worst idea in the world to just double check that the domain of G and the range of G sort of properly map onto each other. So the domain of G should become the range of G inverse, and the range of G should become the domain of G inverse. And if they don't, then the initial function's domain might need restricted so that the two functions can truly be inverses, or vice versa. So anyway, what are these going to be? The domain of the original function G is all real numbers, except for the 0 of its denominator, which is 1. Alright, let's look at this guy. What's this guy's range? Well, we talked about how when the numerator and denominator have the same degree, the degree is 1, they're both degree 1 because they're both linear, then your horizontal asymptote is at 1 over 1, which means I'm expecting this graph to be a hyperbola with a horizontal asymptote at 1, which means this guy's range is every number in the world except for 1. So far so good for our function and our inverse function having the same domain and range. Now for the range of this function, well again you'd check and see degree 1, degree 1, 1 over negative 1 seems to imply that our horizontal asymptote's at negative 1, so the only output that we'll never get is negative 1. And then, good news, this guy's denominator has a 0 of negative 1, so that means the only element not in this guy's domain is negative 1. Which means that yes, everything's hunky-dory here, and that G and G inverse are inverses without either function needing a restriction on its domain. Okay? That's it for all that. Moving on. 5. What is the relationship between one-to-one functions, inverse functions, and the horizontal line test? That's a great question. I guess we would say something like a function is a one-to-one function if and only if it passes the vertical line test to be a function and the horizontal line test to be one-to-one. Then if a function is a one-to-one function, then that function's inverse is also a function, period. That's it. Alright, so picture being worth 1,000 words. Here's a graph. It goes like this. Is that graph representative of a one-to-one function? And the answer is yes, because if I take a vertical line and drag it across, it never touches more than once. So we pass the vertical line test, so we're a function. Now take a horizontal line and run that across the function, and it never crosses more than once. So that means this thing is a one-to-one function. And that means if I was to take it and reflect it over the line y equals x, and I don't know why I did this, this is going to be annoying to draw, But if I reflect this, then I should get a graph that goes something like that. And you can see that because the original function passed the horizontal line test, this new purple thing passes the vertical line test and therefore is a function. So if this was the original function f, then this purple thing is representative of f inverse, and they are both functions. As opposed to something like this. Yoink. So this is function g, and it is a function because it passes the vertical line test, but it surely fails the horizontal line test. And that's problematic because now if we let this graph be reflected over the line y equals x, then we get this. And that's g inverse. And all of those lines that caused the original function g to fail the horizontal line test, all of those lines can be reflected over the line y equals x, and they become vertical lines that cause g inverse to fail the vertical line test. And that's why g inverse is definitely not a function. And you know that just by looking at the original function g. It's not one-to-one, so its inverse is not a function. That's supposed to be the moral of the story in number 5. All right, moving on. Oh, we're done. Great. I hope you enjoyed another hour-long video. Watch only the parts you need to watch. See you in class. Bye.